Welcome to Chapter 11, Aircraft Performance. In this chapter, we'll explore the fundamental principles that determine how an aircraft behaves throughout every phase of flight. From the moment the throttle is advanced for takeoff to the final moments of landing rollout, a complex interaction of physical laws, atmospheric conditions, and aircraft design characteristics shapes every aspect of performance. We'll examine how factors like air density, temperature, weight, and wind influence what an aircraft can and cannot do. You'll also learn how to interpret and apply performance data, the charts, graphs, and tables found in aircraft flight manuals, so you can make informed, accurate decisions before and during flight. A solid understanding of aircraft performance is not just an academic exercise. It's a critical safety skill that every pilot must master. Let's get started. This chapter covers 4 interconnected areas of aviation knowledge that are essential for safe and informed flight operations. We'll begin with atmosphere and pressure, where we'll examine the structure of the atmosphere, the standard atmosphere model, and the concepts of pressure altitude and density altitude. From there, we'll move into flight performance, covering how an aircraft maintains straight and level flight, the role of drag, climb performance, and how to optimize range and endurance. Our third topic focuses on takeoff and landing, including runway surface factors, the dangers of hydroplaning, and how variables like weight and wind affect your performance speeds. Finally, we'll work through performance charts, where you'll learn how to read, interpolate, and correctly apply data from the Aircraft Flight Manual and Pilot's Operating Handbook to real-world flight planning decisions. Each of these topics builds on the last, so a solid understanding of atmospheric conditions directly informs how you interpret performance data and make go or no-go decisions. Let's get started. Performance data found in the Airplane Flight Manual, or Pilot's Operating Handbook, isn't optional reading. It's mandatory information that directly supports safe and efficient flight operations. The performance section covers everything you'll need across all phases of flight, including takeoff and landing distances, climb rates, fuel consumption, cruise range, and endurance. It also accounts for the critical variables that affect aircraft performance: weight, altitude, and temperature. Understanding this data is essential because performance doesn't exist in a vacuum. A takeoff distance calculated at sea level on a cool morning will look very different from one at a high-elevation airport on a hot afternoon. The data gives you the tools to account for those differences before you ever advance the throttle. One important point to keep in mind: this data is presented in either tabular or graph format, and the format and methodology are not standardized across manufacturers. Each aircraft's performance section may be structured differently, and the assumptions built into that data can vary. Before you apply any performance figure to a real-world scenario, make sure you understand the conditions and assumptions the manufacturer used to derive it. Misreading or misapplying that data can lead to significant errors in your planning, with potentially serious consequences. The atmosphere is made up of a mixture of gases, with nitrogen accounting for roughly 78% and oxygen making up about 21%. The remaining 1% consists of trace gases such as argon and helium. One critical point for aviators is that the majority of usable oxygen exists below 35,000 feet, a fact that has direct implications for both human physiology and engine performance at altitude. From a physical standpoint, air behaves as a fluid. It has mass and weight, and like any fluid, it will flow and change shape in response to even the slightest pressure differences. This fluid behavior is fundamental to understanding how aircraft generate lift and how control surfaces produce their intended effects. The most important takeaway for performance planning is the relationship between air density and aircraft capability. As altitude increases, air becomes less dense, and that reduction in density has a cascading effect. Engine power output drops, propeller thrust decreases, and the wings generate less lift. Every phase of flight, from takeoff distance to climb rate to cruise performance, is influenced by the density of the air your aircraft is operating in. Understanding this relationship is essential for making sound, safe performance decisions. At sea level, under standard conditions, the atmosphere has a temperature of 59 degrees Fahrenheit, or 15 degrees Celsius, and a pressure of 29.92 inches of mercury, which is equivalent to 1013.2 millibars. The weight of that air pressing down on every square inch of surface is 14.7 pounds. As you climb in altitude, both temperature and pressure decrease at predictable rates. Temperature drops at 3.5 degrees Fahrenheit, or 2 degrees Celsius, for every 1,000 feet of altitude gained, up to 36,000 feet. Pressure decreases at roughly 1 inch of mercury for every 1,000 feet, up to 10,000 feet. These values aren't arbitrary. They form the basis of the International Standard Atmosphere, or ICAO, established by the International Civil Aviation Organization, known as ICAO. The ISA gives pilots, engineers, and air traffic controllers a common reference point for calculating aircraft performance, calibrating instruments, and ensuring consistency across aviation worldwide. Keep in mind that real-world atmospheric conditions will often differ from these standards, and understanding that difference is essential for accurate performance planning. Pressure altitude is one of the most fundamental concepts in aviation performance and flight planning, so it is important to understand exactly what it represents and how to determine it. Pressure altitude is defined as the height above the standard datum plane, a theoretical level where atmospheric pressure equals 29.92 inches of mercury and air weighs 14.7 pounds per square inch. In other words, it tells you where you are in relation to a standardized atmosphere, rather than your actual height above the ground or sea level. There are 3 practical ways to determine pressure altitude. The simplest method is to set your altimeter's Kollsman window to 29.92 and read the indicated altitude directly. You can also apply a correction factor to your field elevation using the altimeter setting conversion table. A flight computer can also be used to calculate it quickly. Understanding why this matters is just as important as knowing how to find it. Pressure altitude is the baseline for all aircraft performance charts. Things like takeoff distance, climb rate, and density altitude calculations all start here. It is also the reference used when assigning flight levels above 18,000 feet, where all aircraft transition to a standard altimeter setting of 29.92. Mastering this concept will directly improve the accuracy of your performance planning. Density altitude is one of the most critical concepts in aviation performance planning, and understanding it correctly can be the difference between a safe departure and a dangerous one. By definition, density altitude is pressure altitude corrected for non-standard temperature. It represents the altitude at which the aircraft's performance will correspond in a standard atmosphere, making it the most accurate measure of aerodynamic performance when conditions deviate from standard. The key relationships are straightforward but essential to internalize. As density altitude increases, the air becomes thinner and aircraft performance decreases across the board. Think reduced lift, reduced thrust, and reduced engine power. Conversely, lower density altitude means denser air and improved performance. Remember that air density varies directly with pressure and inversely with temperature. Higher temperatures reduce density, which drives density altitude up, even when you haven't physically climbed any higher. Consider this practical example. At a field with a pressure altitude of 5,000 feet and an outside air temperature 20 degrees Celsius above standard, your density altitude could exceed 7,000 feet. That difference alone can increase your takeoff ground roll from roughly 790 feet to over 1,000 feet. That's a significant performance penalty that must be accounted for during pre-flight planning, particularly at high-elevation airports on hot days. Density altitude is directly influenced by 3 atmospheric variables: pressure, temperature, and humidity. Understanding how each one affects air density is essential for making sound performance decisions. Starting with pressure, density and pressure are directly proportional. If you double the pressure while keeping temperature constant, you double the density. As you climb in altitude, pressure drops, and so does air density. This is why aircraft performance decreases at higher elevations. Temperature works in the opposite way. It has an inverse relationship with density. As temperature increases, air molecules spread apart, reducing density. Both pressure and temperature decrease with altitude, but the pressure drop is the dominant factor. Humidity is often underestimated. Water vapor is actually lighter than dry air, so as moisture content increases, overall air density decreases. This raises your density altitude and reduces aircraft performance, even on a day when your altimeter reading might seem acceptable. The key takeaway is this. High-density altitude conditions occur when you have high elevation, low pressure, high temperature, high humidity, or any combination of these factors. When multiple conditions stack together, performance degradation compounds. Always evaluate all three variables together before flight, not just one in isolation. In straight and level flight, the aircraft must satisfy two equilibrium conditions simultaneously. Lift must equal weight to maintain altitude, and thrust must equal drag to maintain a constant airspeed. When either of these conditions is disrupted, the aircraft will accelerate, decelerate, climb, or descend. Now, drag itself comes in two distinct forms. Induced drag is generated as a byproduct of lift production from the wings and other lifting surfaces. It dominates at low airspeeds, where the wings must work harder to generate the required lift. Parasite drag, on the other hand, comes from all non-lifting surfaces, the fuselage, landing gear, antennas, and so on, and it dominates at higher airspeeds. The relationship between speed and drag is not linear, and this is a critical concept. If you double your airspeed, parasite drag increases fourfold, and the power required to overcome it increases eightfold. Meanwhile, induced drag drops to just 1/4 of its original value. This inverse relationship means there is a specific airspeed where total drag is minimized, and that point has important implications for range and endurance. Finally, maximum level flight speed is reached when the power or thrust required to fly equals the maximum power or thrust the engine can deliver. Any additional drag beyond that point cannot be overcome. When climbing, pilots must choose between two distinct performance objectives, and understanding the aerodynamic principles behind each will help you make the right decision at the right time. Angle of climb, flown at Vx, gives you the greatest altitude gain over a given horizontal distance. This is critical when you need to clear obstacles immediately after a short field takeoff. AOC depends on excess thrust, the thrust available beyond what is required to maintain level flight. For jet aircraft, maximum excess thrust occurs near L over D max, which is where induced and parasite drag are balanced. For propeller aircraft, that peak actually occurs below L over D max. Rate of climb, flown at Vy, gives you the greatest altitude gain per unit of time, making it ideal when air traffic control assigns you a specific altitude and you need to reach it efficiently. ROC depends on excess power rather than excess thrust. Here the relationship flips. Jet aircraft achieve maximum excess power above L over D max, while propeller aircraft achieve it near L over D max. The key takeaway is that AOC and ROC are not the same thing, and they are not achieved at the same airspeed. Knowing which one you need and why directly impacts both safety and efficiency in climb operations. Three major factors influence climb performance: weight, altitude, and aircraft configuration. Starting with weight, as aircraft weight increases, induced drag rises, which directly reduces the excess thrust and excess power available for climbing. A heavier aircraft also requires a higher airspeed to achieve its best rate of climb, yet despite flying faster, the actual climb rate achieved is lower than it would be at a lighter weight. More weight means less climb capability. Altitude has a compounding effect on climb performance. As you climb higher, the power required increases while the power available from your engine decreases due to the thinning atmosphere. This causes Vx and Vy to gradually converge. At the absolute ceiling, they meet at a single point, the only airspeed where steady level flight is even possible, and at that altitude, your rate of climb equals 0. Configuration matters as well. Extending the landing gear or deploying flaps increases drag, reducing both excess thrust and excess power. This degrades your maximum angle of climb and maximum rate of climb simultaneously, which is why clean configuration is essential for optimum climb performance. Understanding the two ceiling definitions is critical. The service ceiling is the altitude where your aircraft can no longer climb faster than 100 feet per minute. The absolute ceiling is the theoretical maximum, where rate of climb reaches zero and sustained level flight at only one precise airspeed is all that remains. Range and endurance are two distinct performance goals, and understanding the difference is essential for efficient flight planning. Range refers to the distance you can cover per pound of fuel, expressed in nautical miles per pound. Endurance, on the other hand, refers to how long you can remain airborne per pound of fuel, expressed in hours per pound. These are related but not the same, and optimizing for one does not automatically optimize for the other. To maximize endurance, you want to fly at the minimum power required condition, which corresponds to the lowest possible fuel flow. This keeps you airborne the longest, but does not necessarily cover the most ground. To maximize range, you fly at L/D maximum, which gives you the best ratio of speed to power and the greatest distance per unit of fuel burned. In practical operations, pilots often use a long-range cruise technique, which targets 99% of maximum specific range. This small sacrifice in efficiency yields a 3 to 5% increase in airspeed, making the trade-off worthwhile on most flights. It is also important to recognize that specific range is not a fixed value. It changes with aircraft gross weight, altitude, and external aerodynamic configuration. As fuel burns off and weight decreases, or as you climb to a more favorable altitude, your specific range will shift accordingly. Monitoring these variables allows you to make informed adjustments throughout the flight. In normal flight operations, the relationship between airspeed and power is straightforward. If you want to fly faster, you add power. If you slow down, you reduce power. This is the region where the vast majority of flight takes place, including climbs, cruise, and maneuvering flight. However, below the speed for minimum power required, which corresponds to best endurance speed, that relationship reverses. In this region, as airspeed decreases, you actually need more power just to maintain level flight. This is what we call the region of reversed command, and the lower boundary of this region is stall speed. The practical danger here is significant. Pilots flying slow, stabilized approaches to short or soft fields can unknowingly enter this region. If the aircraft begins to sink and the pilot instinctively lowers the nose to arrest that sink rate, the response is counterproductive. The sink rate actually increases. The correct response is to add power immediately and restore proper airspeed. Operating in the region of reversed command demands precise airspeed control and a thorough understanding of power management. Recognizing when you are on the backside of the power curve and knowing how to respond is a critical element of safe flight, particularly during low and slow operations near the ground. Understanding the key variables that affect takeoff and landing performance is essential to safe flight operations, and it begins with one fundamental concept. Your takeoff and landing speed is directly tied to your stall speed. The relationship between speed and energy is not linear. It's exponential. An aircraft traveling at 75 knots carries 4 times the kinetic energy of one moving at 37 knots. This matters enormously because stopping distance scales with the square of your speed. Even a modest increase in airspeed translates to a significantly longer ground roll to stop the aircraft. The 3 primary factors governing your roll distance are your takeoff or landing speed, your rate of acceleration or deceleration, and the resulting distance those 2 variables combine to produce. All 3 must be considered together when evaluating runway requirements. This is not an academic exercise. The majority of pilot-caused accidents occurred during the takeoff and landing phase of flight, making this the highest-risk portion of any operation. It's also critical to understand what your performance charts are actually telling you. Those published numbers assume a paved, level, smooth, and dry runway under standard atmospheric conditions, with an aircraft in good working order and a pilot of average skill. Any deviation from those assumptions means your actual performance will differ, and in most real-world conditions, it will require more runway, not less. Runway surface and gradient are 2 environmental factors that can significantly affect your takeoff and landing performance, and both deserve careful consideration during your pre-flight planning. Starting with surface effects, any surface that isn't a firm, dry, paved runway will increase your ground roll. Soft, grassy, or muddy surfaces create additional rolling resistance under the tires, which reduces acceleration and extends the distance needed to reach flying speed. Standing water, snow, and mud compound this further. As a practical rule, when operating from dry grass, you should increase your distances by 20% of the 50-foot obstacle clearance figure from your performance charts. Runway gradient refers to the slope of the runway, expressed as a percentage. A 3% gradient means the elevation changes 3 feet for every 100 feet of runway length. When departing upslope, gravity is working against you, so expect a longer takeoff roll. However, that same upslope works in your favor on landing, helping to slow the aircraft and shortening your landing roll. The opposite is true for a downslope runway. You'll accelerate faster on takeoff, but require more distance to stop on landing. You can find both runway surface type and gradient data in the Chart Supplement US, so make it a habit to look up this information for any unfamiliar airport before you fly. Dynamic hydroplaning is one of the most serious hazards you can encounter during landing on a wet runway, and understanding it could save your life. It occurs when your aircraft's tires ride up onto a thin film of water, completely losing contact with the runway surface. When this happens, braking effectiveness and directional control drop to nearly zero. You are essentially skating on water with limited ability to stop or steer the aircraft. The hydroplaning speed formula gives you a critical reference point. Take the square root of your tire's inflation pressure in PSI and multiply by 9. For a tire inflated to 36 psi, that's the square root of 36, which is 6, multiplied by 9, giving you 54 knots as the minimum speed at which hydroplaning can begin. Prevention starts before touchdown. Land into the wind to maximize directional control, and use aerodynamic braking to its fullest advantage before relying on wheel brakes. Avoid any abrupt control inputs on wet runways. One critical point to remember: once hydroplaning begins, it can continue well below the speed at which it started, so do not assume you have regained control simply because you have slowed down. Finally, never underestimate the impact of excess speed. Landing just 10% above your recommended speed results in at least a 21% increase in landing distance. On a wet runway, that margin can make all the difference. Takeoff performance is influenced by several critical factors that every pilot must understand before calculating their required runway distance. Let's start with gross weight. A seemingly modest 10% increase in takeoff weight has a compounding effect on performance. It raises your liftoff speed by 5%, reduces acceleration by 9%, and increases your takeoff distance by at least 21%. To put that in practical terms, a Cessna 182 loaded to 2,700 pounds instead of 2,400 pounds needs 575 feet to get airborne. That's 135 feet more than at the lighter weight. Small weight differences add up quickly. Wind is equally significant. A headwind equal to just 10% of your takeoff speed reduces the required distance by roughly 19%. Conversely, a tailwind of the same magnitude increases your distance by about 21%. A strong 50% headwind can cut your takeoff roll by as much as 75%. Always know your wind direction and magnitude before committing to a runway. Finally, density altitude affects performance in two ways simultaneously. At higher density altitudes, your aircraft must achieve a greater true airspeed to generate the same indicated airspeed needed for liftoff, and your engine produces less thrust. Both effects combine to dramatically increase takeoff distance. Always compute density altitude and apply the appropriate performance corrections before every departure. Several critical factors affect how much runway you'll need to land safely, and understanding each one helps you make smart decisions before you ever touch down. First, gross weight. A 10% increase in weight raises your landing speed by 5%, which in turn increases your landing distance by 10%. Heavier aircraft simply need more runway, so always know your landing weight before you arrive. Wind is another major factor. A tailwind of just 10 knots can increase your landing distance by approximately 21%. That's a significant penalty, and it's why you should always land into the wind whenever conditions and traffic allow. Density altitude affects landing performance in the same way it affects takeoff. For every 1,000 feet of field elevation, expect roughly 3.5% more landing distance. At 5,000 feet, you're already looking at about 16% more runway than you'd need at sea level. Finally, and perhaps most importantly, watch your approach speed. Crossing the threshold at just 10% above your target speed causes at least a 21% increase in landing distance, and it accelerates brake wear significantly. Fly a stabilized approach at the correct speed every time. These factors can combine quickly, so always run the numbers and never assume the runway you have is more than enough. Understanding performance speeds is fundamental to safe flight operations. These reference speeds, known as V-speeds, define the boundaries within which an aircraft is designed to operate safely. Starting with stall speeds, VS0 is the stall speed in the landing configuration with power off, while VS1 refers to stall speed in any other specified configuration. Knowing these keeps you above the threshold for controlled flight. For climb performance, VX gives you the best angle of climb, meaning the most altitude gained over a given horizontal distance, critical for obstacle clearance after takeoff. VY gives you the best rate of climb, maximizing altitude gain over time, your go-to speed for a normal climb to cruise altitude. VA, the maneuvering speed, is especially important. At or below this speed, you can apply full control inputs without risking structural damage. Above VA, aggressive or combined control movements can overstress the airframe. VFE, VLE, and VLO govern your flap and landing gear operations. Exceed these speeds with systems extended or in transition, and you risk mechanical damage. Always check these before configuring the aircraft. Finally, VNO is your maximum structural cruising speed for normal operations, and VNE is the absolute never exceed speed. Operating above VNE risks structural failure. These are hard limits, not guidelines. Commit these speeds to memory. Your safety depends on it. There are 4 airspeed types you need to understand, and each one builds on the last. Starting with indicated airspeed, or IAS. This is the raw value displayed on your airspeed indicator. It has not been corrected for any instrument error, position error, or compressibility effects. Next is calibrated airspeed, or CAS, which takes IAS and applies corrections for those position and instrument errors. Importantly, CAS equals true airspeed at sea level in a standard atmosphere. Moving up, equivalent airspeed, or EAS, takes KAS one step further by correcting for adiabatic compressible flow at altitude. Like CAS, EAS equals true airspeed at sea level, so the difference only becomes meaningful as you climb higher. Finally, true airspeed, or TAS, represents the aircraft's actual speed relative to the surrounding air mass. Because air density decreases with altitude, TAS will always be greater than IAS at altitude. The instrument underreads because the air is thinner. Understanding how these 4 values relate to one another is fundamental to interpreting aircraft performance data correctly and applying it safely across different altitudes and atmospheric conditions. Performance charts are one of the most important planning tools available to a pilot. They tell you exactly what your aircraft is capable of under specific conditions, including how much runway you will need for takeoff and landing, how much fuel the flight will require, how long it will take to reach your destination, and what climb rates, cruise speeds, and range you can expect. These charts come in several formats. Some use a simple table layout where you look up your conditions directly. Others use a graph format where you trace lines across axes to find your answer. More complex charts combine multiple variables onto a single diagram, requiring you to work through several steps before arriving at your final value. Here is something every pilot must understand about chart data. Those numbers were obtained from test flights conducted in brand new aircraft, flown by pilots with average skill levels, using properly functioning equipment. That means real-world performance may fall short of what the chart shows. For that reason, you must read all conditions and notes on every chart before using it. Compensate whenever your situation differs from the standard conditions assumed in the chart, and compute performance values before every single flight, not just when conditions seem challenging. Always apply a conservative bias by selecting slightly adverse values to build in a safety margin. Performance planning is not a formality. It is a fundamental part of safe flight preparation. Let's walk through a sample density altitude problem using real numbers so you can see exactly how this process works in practice. Our airport sits at an elevation of 5,883 feet. The outside air temperature is 70 degrees Fahrenheit, and our altimeter setting is 30.10 inches of mercury. We start by finding our pressure altitude. Locate 30.10 in the altimeter correction table. That gives us a correction factor of negative 165 feet. Subtract that from field elevation, 5,883 minus 165, and we get a pressure altitude of 5,718 feet. Now take that value to the density altitude chart. Find 70 degrees Fahrenheit along the bottom axis. Move straight up until you intersect the 5,718-foot pressure altitude line. Then read horizontally across to the density altitude scale on the left. The result is approximately 7,700 feet. Think about what that means. The aircraft is sitting at an airport less than 6,000 feet above sea level, but it will perform as though it were operating at 7,700 feet. That difference of nearly 1,800 feet has real consequences for takeoff distance, climb rate, and engine performance. This is exactly why you must calculate density altitude before every flight, particularly on warm days at elevated airports. Let's work through a second sample problem using the combined takeoff distance graph. For this scenario, we have a pressure altitude of 2,000 feet, an outside air temperature of 22 degrees Celsius, a takeoff weight of 2,600 pounds, a headwind of 6 knots, and we need to clear a 50-foot obstacle. Entering the graph with these conditions, we arrive at a ground roll distance of 700 feet. To clear the 50-foot obstacle, the total distance required increases to 1,400 feet. Notice how the obstacle clearance requirement effectively doubles the ground roll in this case, a reminder of just how significantly that additional climb requirement impacts your planning. The graph also gives us critical speed information. At 2,600 pounds, our liftoff speed is 63 knots, and we need to be at 68 knots as we cross the obstacle. These reference speeds are essential for flying an accurate and safe departure profile. Always confirm these values from your specific aircraft's performance charts, as they vary with weight and configuration. Use both the distance figures and the speed callouts together to build a complete picture of your takeoff performance. Let's walk through sample problem 3 using the table method for a short field takeoff. Our conditions are a pressure altitude of 3,000 feet, an outside air temperature of 30 degrees Celsius, an aircraft weight of 2,400 pounds, and an 18-knot headwind. Looking up these values in the performance table, we get a ground roll of 1,325 feet and a total distance to clear a 50-foot obstacle of 2,480 feet. But we're not done yet. We still need to account for that headwind. The notes section of the table tells us to decrease the distances by 10% for every 9 knots of headwind. With 18 knots, that's 2 increments, giving us a 20% total reduction. Multiply both values by 0.80. The ground roll comes down to 1,060 feet, and the total distance over the 50-foot obstacle becomes 1,984 feet. Now, a word on interpolation. If your exact pressure altitude isn't listed in the table, you'll average the values from the 2 surrounding altitudes to estimate your performance. When in doubt, always round toward the more adverse condition, meaning the higher, more conservative number. This gives you a built-in safety margin and keeps your planning on the conservative side, which is exactly where it should be. Now, let's work through sample problem 4 using the graph method for climb performance. In this scenario, we are departing from a pressure altitude of 6,000 feet at 25 degrees Celsius and climbing to a cruise pressure altitude of 10,000 feet at 10 degrees Celsius. The key technique here is that we don't simply read values at the cruise altitude. Instead, we read the chart values at both altitudes and subtract the lower from the upper. This accounts for the fact that the chart builds cumulative values from sea level, so we need to isolate only the portion of the climb we're actually flying. Working through the numbers, for fuel, we read 6.0 gallons at 10,000 feet and 3.5 gallons at 6,000 feet, giving us 2.5 gallons consumed during the climb. For time, 10.5 minutes minus x minutes equals 4.5 minutes. And for distance, 15 nautical miles minus 9 nautical miles gives us 6 nautical miles covered during the climb. One critical point. These chart values assume maximum continuous power and zero wind conditions. In practice, you'll need to adjust your planning accordingly. A headwind will reduce your ground distance covered during the climb, while a tailwind will increase it. Always account for actual conditions when applying these figures to your flight planning. Let's work through a complete climb table problem using realistic flight conditions. Our departure pressure altitude is sea level. The outside air temperature is 22 degrees Celsius, and we're climbing to a cruise pressure altitude of 8,000 feet at a weight of 3,400 pounds. When we look up these conditions in the climb table, we get our baseline results before any temperature correction. 10 minutes of climb time, 21 pounds of fuel used, and 20 nautical miles covered. Now, here's the critical step. Standard temperature at sea level is 15 degrees Celsius, and our actual OAT is 22 degrees. That's 7 degrees above standard. The climb table tells us to add 10% for each 7 degrees above standard, so we apply exactly one 10% correction across all three values. 10 minutes becomes 11 minutes. 21 pounds of fuel becomes 23.1 pounds. And 20 nautical miles becomes 22 nautical miles. One final conversion worth noting, aviation fuel weighs approximately 6 pounds per gallon, so dividing 23.1 pounds by 6 gives us 3.85 gallons. You'll need this conversion anytime your fuel planning is done in gallons rather than pounds. Always apply the temperature correction before converting units. Let's work through two practical examples using cruise and range performance tables. In sample problem 6, we're flying at a pressure altitude of 5,000 feet with 2,400 RPM, and we have 38 gallons of usable fuel with no reserve. Looking up those conditions in the cruise table, we find a true airspeed of 116 miles per hour, a fuel burn rate of 6.9 gallons per hour, an endurance of 5.5 hours, and a total range of 635 miles. Notice how endurance and range are directly tied to your fuel load. Always confirm you're using the correct usable fuel figure. In sample problem 7, we shift to a higher performance scenario at 6,000 feet with an outside air temperature 36 degrees Fahrenheit above standard, which equals ISA plus 20 degrees Celsius. Using the appropriate non-standard temperature column in the cruise power table, we find the recommended power setting calls for 2,450 Rn, delivering 65% continuous power at a manifold pressure of 21.0 inches of mercury. Fuel flow increases to 11.5 gallons per hour, and true airspeed rises to 161 knots. This example reinforces why temperature must be accounted for. Non-standard conditions directly affect power output and efficiency. Let's work through two sample problems using the range and cruise performance charts. In sample problem 8, we have standard OAT, a pressure altitude of 5,000 feet, and 65% power. Reading the range graph, we get approximately 522 miles with reserve fuel and 581 miles without reserve. That difference highlights why it's important to know which figure you're working with. Range with reserve is the conservative practical number you'd use for flight planning purposes. Moving to sample problem 9, we're using the cruise performance graph with an OAT of 16 degrees Celsius, a pressure altitude of 6,000 feet, and 65% best power mixture. The chart gives us a true airspeed of 140 knots. However, this aircraft does not have wheel fairings installed, so we need to apply a correction. The chart notes tell us to subtract 8 knots for the absence of fairings, bringing our actual true airspeed down to 132 knots. This is a critical habit to develop. Always read the chart notes carefully before accepting any value as your final answer. Corrections for equipment differences like wheel fairings can meaningfully affect your performance numbers and must be accounted for in your planning. When operating in crosswind conditions, it's important to understand how your aircraft was certified and what its published limits actually mean. Certification standards require that aircraft be tested in 90-degree crosswinds up to 20% of VSO, which is the stall speed in the landing configuration. The maximum demonstrated crosswind component resulting from that testing is then published in the Airplane Flight Manual or Pilot's Operating Handbook. Never exceed that value. Let's work through sample problem 10 to see how the chart is used in practice. The runway in use is runway 17, which has a magnetic heading of 170 degrees. The reported wind is from 140 degrees at 25 knots. To find the wind angle, subtract the wind direction from the runway heading. 170 minus 140 gives us a 30-degree angle. Entering the chart with 25 knots and a 30-degree angle, we find a headwind component of approximately 22 knots and a crosswind component of approximately 13 knots. Always verify that the crosswind component falls within your aircraft's demonstrated limit before proceeding with the approach and landing. Exceeding that limit puts you outside the envelope the manufacturer has validated. Let's work through two more practical examples using landing distance charts. In sample problem 11, we encounter a pressure altitude of 1,250 feet, which falls exactly halfway between the sea level and 2,500-foot entries on the chart. Because it sits at the midpoint, we simply take the average of those two values. This is a straightforward interpolation that gives us a precise answer without needing complex math. Moving to sample problem 12, we're using a combined graph with the following conditions: an outside air temperature of 57 degrees Fahrenheit, a pressure altitude of 4,000 feet, a landing weight of 2,400 pounds, a 6-knot headwind, and a 50-foot obstacle. Working through the chart with those inputs gives us a ground roll of 975 feet and a total landing distance over the 50-foot obstacle of 1,000 feet. Here's a critical point to remember. Your landing weight will almost always be less than your takeoff weight because you've burned fuel during the flight. Never assume these numbers are the same. Before solving any landing distance problem, recalculate your actual landing weight by accounting for fuel consumed. Using an incorrect weight will give you inaccurate distance figures and could compromise safety. Let's work through sample problem 13 using the stall speed performance chart. Our conditions are power off, flaps down, gear down, and a bank angle of 45 degrees. We go to the gear and flaps down, power off row, and read across to the 45-degree bank column, which gives us a stall speed of 78 miles per hour or 68 knots. Notice how dramatically stall speed changes as bank angle increases. In straight and level flight, that same configuration stalls at just 66 miles per hour. By the time you reach a 60-degree bank, stall speed jumps all the way to 93 miles per hour. That's a significant increase, and it's directly caused by the increased load factor in a banked turn. Also take a moment to compare the three configuration rows. With gear and flaps up, the aircraft stalls at higher speeds across the board. Adding full flaps and gear, combined with power on, gives you the lowest stall speeds. Understanding how configuration, bank angle, and power setting each affect stall speed is essential for safe maneuvering flight, especially when flying slow in the traffic pattern or during approach turns. Let's walk through a scenario that shows exactly how quickly a series of small, seemingly manageable errors can stack into a catastrophic outcome. A pilot accepts a runway change to runway 27 while already established downwind for runway 18. There's light rain, a 10-knot tailwind from the east, the aircraft touches down 1,000 feet past the threshold, and the airspeed at touchdown is 80 knots instead of the target's 70. Now watch how the numbers build. That 10% excess airspeed alone increases landing distance by 20%, pushing the required distance from 1,000 feet to 1,120 feet. The 10-knot tailwind adds another 20%, bringing the requirement to 2,240 feet. Add back the 1,000-foot overshoot, and the pilot now needs 3,240 feet of a 3,500-foot runway, leaving just 260 feet of margin. Then hydroplaning enters the picture. On a wet surface, locked brakes can cause the aircraft to skid an additional 300 to 500 feet. That 260-foot margin disappears entirely. This is the danger of compounding errors. No single factor here was catastrophic on its own, but each one multiplied the effect of the next. Aeronautical decision-making isn't just about individual choices. It's about recognizing when a chain of decisions is leading you toward a point of no return and acting before that point arrives. Transport category aircraft are held to the most rigorous certification standards in aviation. Fixed-wing transport category aircraft are certificated under 14 CFR Part 25, while transport category helicopters fall under 14 CFR Part 29. These regulations establish the performance and airworthiness baseline that operators and pilots must understand and work within. For deeper study, the Airplane Flying Handbook and the Instrument Procedures Handbook are essential references, particularly the Instrument Procedures Handbook when it comes to obstacle clearance requirements during departures and arrivals. As these aircraft grow more capable and complex, computerized flight mission planning systems have become an integral part of operations, both during pre-flight planning on the ground and through onboard systems in flight. These tools are powerful, but they are only as reliable as the pilot's understanding of them. That brings us to a critical point about pilot responsibility. You must become intimately familiar with any mission planning programs you use, understand the performance characteristics and limitations of your specific aircraft, and know how every onboard computerized system operates. However, regardless of what any planning tool tells you, the Aircraft Flight Manual or Pilot's Operating Handbook remains your primary and authoritative source for performance data. Never allow automation to substitute for your own informed judgment. As we wrap up Chapter 11, let's reinforce the core concepts that every pilot must carry with them on every flight. The atmosphere sets the stage for everything. Pressure, temperature, and humidity combine to determine density altitude. And density altitude is what your aircraft actually responds to, not what the altimeter reads. Understanding that relationship is foundational to predicting real-world performance. Know your V-speed's cold. Vx gets you over obstacles, Vy gets you climbing efficiently, and Vne is a hard limit you never approach. Each speed exists for a reason, and confusing them in a critical moment can be fatal. Weight, wind, and density altitude are your three primary variables when calculating takeoff and landing distances. These conditions change with every flight, which is exactly why performance planning is never optional. It is required every single time. Your AFM and POH are not suggestions. They are the authoritative source for performance data, and you must apply them correctly, reading all notes, interpolating between values, and building in conservative margins. Finally, sound decision-making ties everything together. Errors in performance planning compound quickly, and the runway can run out before you realize the mistake. Remember, the landing phase generates more pilot-caused accidents than any other. Respect the numbers, apply sound judgment, and make performance planning a non-negotiable habit before every flight. You have now completed Chapter 11, and with it, you have built a solid foundation in aircraft performance, one that spans everything from the behavior of the atmosphere to the practical skill of reading and applying performance charts accurately. Remember, this knowledge is not just academic. Every flight you conduct will require you to think critically about density altitude, weight, temperature, pressure, and how those factors combine to affect your aircraft's actual capability. On that day, at that airport, in those conditions, your primary authority is always the Airplane Flight Manual or Pilot's Operating Handbook for your specific aircraft. No general rule of thumb replaces the data found in those pages. Make it a habit to consult your performance charts on every pre-flight planning session, not just when conditions seem challenging. To reinforce what you have learned, practice density altitude calculations regularly, pull out your aircraft's AFM or POH, and work through the performance charts until reading them becomes second nature. And apply these concepts every time you plan a flight. For further study, refer to the FAA Pilot's Handbook of Aeronautical Knowledge, Chapter 11, pages 257 through 284, and supplement that with the Airplane Flying Handbook, FAA H833. Both are essential references for any serious pilot. Well done on completing this chapter.